We're going to talk through some lab results from our kinetics of a clock reaction. This is a second kinetics experiment where we're reinforcing all of the math concepts from our previous week on the iodination of acetone. We're going to see many similarities between last week's lab and this week's. In this particular series of reactions, we have two different equations that we'll be studying. Equation number 1 has the iodide plus the bromate reacting with an acid, H+, which the jar was HCl, forming bromide, molecular iodine, and water. In the kinetics, this is actually the slow step. Now the second equation that's also happening in the beaker is this molecular iodine reacting with the S2O3 2- polyatomic ion, forming 2I- and then the S4O6 2- polyatomic ion. And this, in this two-step equation, is the faster of the two steps. If we notice that both of these equations are indeed occurring, we have happening is the iodide that is consumed in the first reaction is reformed in the second reaction. The molecular iodine that is formed in the first reaction is then consumed in the next reaction. So it's this continuous process of using and then making and then using the iodide, which is the ion name, the iodide ion, back into the molecular form of iodine. And so what happens is this reaction continues until the reactants are consumed and we run out of the individual iodide. Now, in the presence of starch, the molecular iodine that forms here is going to instantly turn blue. So that's really what the clock is about. It's timing how long that I take equation 1 and react it in a beaker, pour it into a separate beaker with equation 2, and see how long it takes for this to go from clear to blue. And I put a little YouTube clip on so you can get a visual of how instantaneous the turn actually is. So because the slow step comes from the first step, our rate equation comes from that particular, this is what we're trying to study, from the slow step. The I negative raised to some power m times the bromate concentration, BrO3 negative, raised to some power n, and the acid, which is the HCl, raised to some power p. Because this first equation is the slow step, this becomes the observed rate law. And technically, since we're not really using a limiting reagent and we're using relative rates, we call it rate prime and K prime. To take the rate, which is truly a relative rate, we're simply taking 100 and dividing by time. It's an arbitrary number just so we can take the reciprocal of time, alrighty, to turn it into a rate. So here on your Prelab, this is just looking at the recipe coming out of your Prelab. This is page 10 that you wrote into your notebook, telling me how many milliliters of each ingredient we need to put together to create a reaction vessel. So I know that in my first beaker, beaker 1, we added potassium iodide. Notice that's the source of the I negative. We added sodium thiosulfate, which, by the way, did not appear in the overall observed rate law, so we just held it constant, 10 all the way down, 10 milliliters. The water was there to create a constant volume of 50 milliliters. So in the first beaker, Ki, Na2S2O3, and water if needed to create a constant volume. In the second beaker, we had two ingredients, potassium bromate and HCl, and this is the beaker that we added the starch indicator as well. And we used anywhere from 1 to 3 drops of the indicator. Remember, it's the starch that turns blue, indicating that the reaction has gone to completion, and it's an instantaneous turn. So again, this is off of page 10 in your Prelab reading, what I would call the ingredient page. How much of each do we mix? I have to put some ingredients into vessel 1, a beaker. and I have to put some ingredients into container number 2. And when I have them all put together, vessel 1 and vessel 2 are created. I pour them together and I start the timer, and I stop as soon as I see the blue color appear. Alrighty, so that's really our general directions. Notice that just as in last week, we have this constant volume. If I look at how many milliliters of each we have each and every time we run all 5 of these trials, if I add all volumes, you're going to see a consistent, constant volume there of 50 mLs. So no matter how I vary each of these ingredients, I always make sure I end with a constant of 50 milliliters. So let's take a peek at some information. I'm now turning to your lab notebook, page 13, where it says Data and Calculations. With data and calculations, we need to record the following information: the time it took for the reaction to go from clear to instantaneously blue, and I put down 50 seconds for trial 1. Trial 2 and trial 3 are 25 seconds. Trial 4 is 12.5 seconds. And for trial 5, I'm just going to say 2 seconds. That's the one that we have to estimate, so I'll just say 2 seconds. What we also need to do is to show the new concentrations for each of these reactants: I negative, bromate, and the acid H+. And this is where it asks us to show our work. M1V1 equal M2V2. And so one at a time we have to kind of go through using this recipe. 10 mils of 0.001 molar. How many molars would that be in a total volume of 50 mils? So let's just take a little opportunity to get that filled in. We'll need that data anyway. Let's tackle the I negative first. When we went to the jar, the I negative was at a concentration of 0.01 molar. It was for trial 1, 3, and 4 that we measured out 10 milliliters of it. Sorry. So my 10 milliliters was the volume I measured out. I'm going to make that neater, I apologize. In trial 1 and in trial 3 and in trial 4, for the iodide, we measured out 10 milliliters of a 0.01 molar solution, but we diluted it to a new volume of 50 milliliters. What is the resulting concentration? So that's where we hit 10. I'll hit this with you. 10 divided by 0.01. I'm sorry. Hit that again. 10 times 0.01. I'm trying to do too many things at once. Divided by 50. So check me out. That's 0.002 molar. All right, through all of that, I think I hit it correctly. So what we just said, notice here, in trial 1, 2, oh, that's the wrong stuff right here. Trial 1, 3, and 4, we used 10 milliliters. Trial 1, 3, and 4 of the iodide. So trial 1, 3, and 4 all had the same value. And here we wrote down 0.002. 0.002, 0.002, and those are all molar units. Notice what we did up here in trial 2. We doubled the volume, so I know that my concentration would double, 0.004 volume. And just to kind of remind myself, in trial 2 then down here, trial 2, we measured out 20 mils of a 0.01 molar, diluted it to a new total volume of 50, and solved for that new concentration. And that's where we showed that that would come out to be 0.004 molar. And what about that very last concentration? In trial 5, we ran it at 8 milliliters. So it's all over the place. At 8 milliliters for trial 5, 8 times 0.01 set equal to 50 times x, where x is going to be the new molarity, and that's 0.0016. I don't know why I'm getting stray lines, but bear with me. 0.0016. So as we looked through and wrote out our concentrations for, this is the I negative, 002, 004, 002, 002, 0016. Now what we're going to have to do as well is all of the other reactants. But you get the idea of what we're doing, very similar to last week. Alrighty. So again, let's work through the common data for the next ingredient. And I'll just change colors here. The next ingredient is bromate. We have to show our work of how we did MV equal MV. Now the original concentration of, if you look back into your data table of bromate, KBrO3, it was 0.04 molar. In our first trial, we measured out 10 mils, diluted it to a total volume of 50. What's the new concentration? So 0.04 times 10 divide by 50, and our new concentration here is 0.008. And I'll go ahead and put that in our data table. Also, let's see where the bromate, trial 1, 2, and 4 will be the same. What about trial 3? Well, trial 3 looked like we doubled the amount. So if we doubled that concentration, we can simply show that by saying 0.04 times 20 set equal to 50 times x. X is going to be that new molarity, and that should come out twice as concentrated, 0.016. Alrighty. And then the very last one, we used 5 milliliters, so that should be half as concentrated. Repeating, because this is getting sloppy, I don't know why it's stray marks. 0.008, 008, 016, 008, 0.004 molar. We have one last, and that's the HCl. It started at 0.1 molar. So this is actually calculating for H+. We started with a 0.1 molar. Trial 1, we measured out 10 milliliters. We diluted it to a total volume of 50. What is the new concentration? 0.1 times 10 over 50 is 0.02 molar. Alrighty, so right here, 0.02 molar, the H+ column. Where did we use 10 milliliters? We used 10 milliliters in trial 1, 2, and 3. And trial 4, we doubled it. So to show that math, 0.1 times 20 is going to be equal to 50 times x. So we could see that that would come out to be 0.04 molar. There, fix the decimal error. 0.02, 0.02, 0.02, 0.04. And with this last trial, we had a volume of 15 mils of the original concentration of 1 molar. We diluted it down, 0.1 molar, diluted it down to a total of 50, what's the resulting concentration? So you're hitting with me a 1 molar at 15 mils would be equal to 50x. And that value came out to 0.3 molar. Now the last thing we should probably do is consider the rate. And perhaps the easiest thing at this time, let's simply add another column over here. And that column should say rate. So we'll just add a little bit of information into a last column. Now remember how we decided we were going to calculate rate as a relative number. We're going to take the number 100 and divide by time. So for instance here, I need to hit 100 over 50, and I'll get a relative rate. 100 over 50 is a relative rate of 2. And that, of course, would be a molarity per second. 100 over 25 would give me a relative rate of 4 molarity per second. 100 over 12.5 gives me a relative rate of 8 molarity per second. And 100, I don't really need this number, but we'll hit it. 100 divided by 2 is a 50 again. So we'll have a relative rate of 50 molarity per second. So this is the information that completes page 13. Alrighty. So what do we know? Remember, our goal was to figure out, with respect to these reactants, the rate is equal to K times the concentration of the iodide raised to M, bromate raised to N, and the acid raised to P. We've calculated a data table that gives us concentrations versus rate. We called this an initial rate data. And what we'd like to do is to make sure we can use trials to compare one to the other. I'm not recording. Yes, I am. I'll edit that out, I hope. 17 minutes, 18 minutes. Write that down. Okay, if I don't get that edited out, I just panicked because I thought I quit recording. Let's go ahead and take a peek at our next page in this is page 14 in our report, to write the relative rate laws for each reaction. And this has a flavor very similar to last week. Rate is equal to K times the concentration of iodide raised to M, some order, times bromate raised to some order N, times the acid ion raised to some order P. We know rate and we know these concentrations. So for instance, the rate we calculated in the first reaction was 2 molarity per second. It's going to be set equal to the rate constant K times the concentration of the iodide in the first reaction raised to the power M times the concentration of, that's 0.08 for the bromate raised to the power N, and then the acid was 0.2 molar raised to the power P. So see what we're going to do each time for the rate laws. We have to copy down the rate that we calculated, which we added on as a separate trial. So we said, for instance, 4 molarity per second is equal to K times the concentration, which was 0.04 this time, raised to the M. The others remain the same, 0.08 times the concentration of the acid, which was 0.2 raised to the power p. We had the same rate, 4 molarity per second is equal to K times that concentration back to 0.02, the concentration from the iodide column. Here we varied the bromate and kept the acid the same. In equation 4, our rate went to 8 molarity per second, set equal to K. Concentration of the iodide remained at 0.02. The bromate went back to 0.08. And here we had doubled the concentration of the acid raised to the P. Alrighty. And you can finish off that fifth equation there. The rate that we found on the previous page, we said was, you'd write that out, rate, which is 50 molarity per second, equal K times 0.016 raised to the M, 0.04 raised to the N, and 0.3 raised to the P. So go ahead and copy that in for that fifth reaction. Now underneath that work, where we simply took the time to write the relative rate, what we need to do now is to compare the trials to find the overall orders with respect to each reactant. So just to remind ourselves, rate is equal to K times the concentration of iodide, which is the power of M, the bromate, which is the power of N, and the acid, which is the power of P. We're being asked to solve for M first. That's the order with respect to iodide. So when I go back to my original data table, what trials should I use to find the relative order for the iodide? This column here is the iodide. What I want to do is to double the iodide as in trial 1 to 2, but notice that the bromate and the acid were kept constant. If the bromate is constant and the acid is constant, it does not influence the change in the reaction rate. From trial 2 to trial 1, we see an influence coming only from the iodide. To find the power with respect to M, we want to compare trial 2 to trial 1. In trial 2, the concentration of iodide was found to be 0.004 molar. The concentration of iodide in trial 1 was found to be 0.002. If I simplify that, 4 over 2, we doubled the concentration. Well, what happened to the rate? In trial 2, which is what we're comparing, the rate was 4 molarity per second, and in trial 1 it was 2 molarity per second, which is a factor of 2. 2 raised to the M power is 2. M, we can see, is a first order reaction. Do the same strategy for N. N is the order with respect to the bromate. What trial should we compare when we're looking back at bromate? Where do we see bromate changing and the others are being held constant? If I compare trial 1, iodide is constant, and in trial 3, the acid is constant, but here I'm noticing I've doubled the bromate. We're going to use trial 1 to trial 3 to find the order with respect to bromate. That's the value of N. And you'll follow that same pattern. We'll say the concentration of bromate in trial 3, 0.0016 molar. And in your next trial that we're comparing, it was originally 0.008. So that's a doubling of the concentration. Notice that my numbers here that I just generated are the same as what's above, 4/2, which is a factor of 2. 2 raised to the n gives me 2. And what does that look like? 2 raised to the n is a first order. So far we have found m is 1 and n is 1, first order with respect to iodide, first order with respect to bromate. How about the p? This is the exponent on the acid. What trials might be most useful in figuring out the order with respect to the acid? So we want to change the acid but hold the others constant. Notice here I'm holding iodide constant between 1 and 4. I'm holding the bromate constant between 1 and 4, but I'm actually doubling the acid in trial 1 to 4. So just to kind of share what that would look like, to find the exponent p, we'd end up saying in trial 4, we're going to compare to trial 1, where the concentration was 0.4 molar for the acid, compared to 0.2 molar, we could see that we doubled the concentration. In terms of rate, in trial 4, the rate was 8 molarity per second. In trial 1, it was 2 molarity per second. That's a factor of 4. 2 raised to the p power gives me 4. That's an exponential rate law, so that looks like a second order overall. 2 squared gives me 4. So we just determined this guy is second order. Rate is equal to K times iodide first order, bromate first order, and the acid is second order. That concludes your page 14. Page 15 is rewriting those rate laws but subbing in the exponents. So example, we found in our first equation the rate was 2 molar per second. We still don't know K. When the concentration of our first reactant was a first order, times the concentration of our second reactant, who was first order, times the concentration of the acid, who was second order. So we're rewriting all of those rate laws from the previous page, but instead of putting m, n, or p, we're actually putting in the exponent on each of those ingredients. For trial 2, we know it was 4 molar per second is equal to K, the constant. This time the concentration of iodide had doubled, first order. The bromate was constant at 0.008, and the acid remained constant at 0.02. We also found a relative rate of 4 for trial 3 when the concentration went back to 0.02, first order, 0.016, first order, 0.02, second order. And we'll do one more, and you can finish off that fifth one. 8 molar per second is K. That concentration back on the iodide in that fourth equation was 0.02. Here we drop back to 0.08 for the bromate, and we finally doubled the concentration of the acid, and it was second order. And there is a trial 5. You can fill that in following these patterns. The next part of this page asks us to actually solve for K, one trial at a time. Solve for K. So if what I'm doing is the algebra up here, solving for K. So I'll show this, my relative rate of 2 divided by 0.002 times 0.008 times 0.02 squared, because it's second order. This number I think will come out big. 2 divided by 0.002 times I'm doing all of that in a parenthesis, by the way. Parenthesis 0.002 times 0.008 times 0.02 squared, close parenthesis, and it's a really big number. I have on my screen 3125000123450. So let's write that out as 3.125 times 10. 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th. Let me count those zeros again. 1, 2, 3, 4, 5. 0.002 times 0.008 times 0.02 squared. So if I hit that correctly, I'm getting an exponent of 1, 2, 3, 4, 5, 6, 7, 8 to the 8th power. And let's see, the unit here, it is a 4th order overall, which gives me m-3 per second. Keep going. You want to keep doing this over and over. The relative rate divided by 0.004 first order times 0.008 first order times 0.02 squared, because it's second order. Let's see how our relative rates compare. So 4 divided by parenthesis 0.004 times 0.008 times 0.02 squared, same number. 3, 1, 2, 5, 1, 2, 3, 4, 5 zeros. So that's 3.125 times 10 to the 8th, whatever you prefer to write. m-3, s-1. I want you to continue to do that for reaction 3, reaction 4, and find the average K. But you'll soon see that because I made this data up, we're going to have a pretty constant K, aren't you? So the average K we'll say is 3.125 times 10 to the 8th power, molarity -3, seconds -1. So you can finish off showing all of that work to find the rate constant and then average. So then it simply says use this to solve for the predicted rate for reaction 5. Alrighty. So let's go back and remember what reaction 5 was actually asking. So I'm going to go back to my first slide. Here are those concentrations for reaction 5. We had 0.016 molar for iodide, 0.004 for bromate, 0.3 for the hydrogen. So that means what I need to do is to plug those numbers in times K and solve for relative rate. Here's what we know. So for the predicted rate, man, just struggling. Predicted rate, we'd like to know rate is equal to K, which we just solved for, 3.125 times 10 to the 8th power times the concentration of the iodide, which we said was 0.016, it was first order, times the concentration of the bromate, which was 0.004, it was first order, and 0.03, which is the acid. Remember, it was second order, so we have to square that. Let's hit that out. I have that number for K still on my screen. So K times 0.016 times 0.004 times 0.03 squared, that number, 0.03 is squared, and my rate is 70312.5 molarity per second, my relative rate. K times those concentrations. Now remember, to get the predicted time, we have to take 100 over rate. 100 over 70312.5. 100 divided by that answer. This is where my made-up numbers fall apart, isn't it? And this is in seconds. That's less than a second. So, oh well. This is my calculated time. And remember what I said, I made up a number earlier. I said, let's just say it took 2 seconds. I knew it would be quick, but less than a second is kind of ridiculous. But that's where it was coming out. So I predicted it would be 0014. And I saw it take 2 seconds, which truly is human error. I can't even click the on and off button on the stopwatch that fast. Turn your page one more to page 16 and just take the difference between our observed rate and the calculated rate, which is pretty much 2 seconds, and a possible source of errors. If you didn't run the lab, I'll tell you a possible source of errors. Not sure exactly when to end the timer, because the reaction, if it didn't instantly turn blue, it faded to blue, and sometimes students were unsure where to end the timing. And secondly, we had difficult time getting the solution to turn blue with consistency because the number of starch drops influenced the rate. So you could not vary the number of starch drops, and some students were doing that. I had to use 1 drop or 2 drops or 3 drops consistently, and if I used different size drops or different numbers of drops, I saw inconsistency in the data as well. That's just some ideas. That concludes your laboratory. You have some post-lab questions you can tackle with that particular information found on page 17. Thanks for listening. I'll try to do some editing, and if I don't get the editing, just bear with me.